Okay, let's discuss the binomial distribution. So the binomial distribution is a very specific kind of discrete probability distribution. And there are a checklist of things that we need to check for in order to identify a particular distribution as specifically binomial. So let's run through some of these things that we need to look for. The binomial experiment is a random experiment which satisfies all of the following conditions. There are only two outcomes on each trial of the experiment. One of the outcomes is usually referred to as a success and the other as a failure. Now, careful with those words. Just because we're calling something a success does not necessarily mean that it's a good thing. It just means that whatever we're focused on in a particular probability experiment, that happens. So, for example, let's say we are looking to see when we spray a bee with poison, does it die? If it dies, we'll consider it a success. If it lives, we'll consider it a failure. So notice that we're talking about death as a success, but in this case, our probability experiment is to see how effective this poison spray is to the bees. Another criteria that we need to check for is that the experiment consists of n identical trials described in condition one. So essentially, it just means that there's a finite number of trials. At some point, we call it quits. The third criteria is that the probability of success from one trial to the next can't change. And we denote probability of success by the letter lowercase p. And the complement to that, which means the exact opposite, would be the probability of failure, which we denote as Q. And Q is 1 minus P. Now, why is it 1 minus P? Well, let's think about that. If I say the probability of success that I am going to get an A on the next math test is a 90% chance. So P would be 0.90. If I wanted to find out what the probability of failure was, how likely is it that I won't get an A on the next math test? Then I would do 1 minus zero point 0.9, and that gives me 0.10, or a 10% chance that I'm going to fail. The next criteria are that all the trials in a binomial experiment need to be independent. Okay, so we didn't go deep into chapter 6, so we didn't discuss independence versus dependence in a probability experiment. So let me quickly run through exactly what that means. Now, being independent means that the trials can be run where you don't need the result of the previous trial to be successful in the next trial. So, for example, let's say that I was putting all of your names into a hat because I had a really cool prize to raffle off. Now, let's say I had multiple prizes. And I take my hand into the hat and pull out my first name, and it's, let's say, John. I say, woohoo, John, you won. Now, for the second prize, I decide that John cannot win again. So I keep John's name out of the hat and go to select the second name. That is dependent trials because the second choice is 100% dependent on who was chosen for the first one. So, since the first one was John, now I know that that directly affects the second trial because John can no longer be selected. If I said it doesn't matter if you win more than once and I put John's name back into the hat, which resets the entire thing to begin trial two, then trial two would be independent of trial one. It would no longer matter that John won trial one because he has a chance to win again in trial two. The last criteria of a binomial experiment is that the random variable has to represent the count of the number of successes. So when we're talking about the random variable, remember we're referring to the x, and we're saying that we are counting successes, not failures or anything else. Okay, here's a rundown of the new symbols we are working with. Some are new, some are not. N is always going to be the sample size, and our samples And binomial experiments are the number of trials that are being done in a particular experiment. P is the probability of success, Q is the probability of failure, and X is that random variable which counts the number of successes in those trials. Okay, so if we're taking a look at this example, we want to determine whether or not this defines a binomial experiment. So a certain surgical procedure has an 85% chance of success. A doctor performs the procedure on 8 patients. The random variable represents the number of successful surgeries. All right, let's run down our criteria. Are there a fixed number of trials? Yes, we have 8 patients. N equals 8. Okay, good. Next, does the probability of success change from trial to trial? Well, we're saying that in general, the surgery has an 85% chance of success, and one patient's success or failure should not affect the next patient's surgery. So, yes, the probability of success remains consistent from trial to trial or patient to patient. Next, we're asking ourselves, does one surgery have any effect on the next surgery? And as I just said, no. Each surgery is different and completely isolated, which means that the trials are independent of each other. And we have defined the variable, the random variable X representing the number of successful surgeries. So with that being said, yes, this is a binomial experiment. I left the solutions in the PowerPoint as well, so you can read them over again. Let's take a look at another example. A jar contains 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select 3 marbles from the jar without replacing, which means I select the first one and it does not get replaced back in when I go to select the second one. The random variable represents the number of red marbles. Okay, there are some things that are good here, and then there's some things that fail. So one thing for you to know is even if you identify that the random variable X is defined as what's supposed to be a success, getting a red marble, that if you find one thing that fails, the whole thing is not a binomial. So it's not about finding one thing correct, it's about either showing all the criteria are correct or that you found one that fails. So if we take a look at this, the trials themselves are not independent, they are dependent trials. Since we are not replacing the marbles back into the jar after we select them, that means whatever color the first marble is does affect the next marble. It also changes the probability of success. We have a total of 20 marbles in this jar. So the moment that you take, oh, well, there's 20 marbles in the jar and there's 5 of them that are red. And since we're focused on red marbles as success, that's why I'm focused on the red ones. So there's a 5 out of 20 chance of getting a red marble when selecting the first marble. But no matter what the color of the first marble is, the denominator is going to go from 20 to 19 and therefore changing the probability of success. And therefore, we're failing. Not only are these not independent, but they're also not keeping a consistent probability of success from trial to trial. Again, I left the answers in the PowerPoint for you to look them over again. Another example. This time we'll use technology to actually calculate a probability. A survey found that 26% of US adults believe there is no difference between secured and unsecured wireless networks. A secured wireless network uses barriers such as firewalls and passwords to protect your information. An unsecure network does not. So, if you're at school, you know that the school requires that you sign in with your student ID and your password, which then gets you behind the firewall, making it more secure. But if you go to McDonald's, it's just open in public, no password needed most of the time, and therefore you are it's much more risky, and hackers can access more of your information, especially if you're on like a bank site on public Wi-Fi. Not a good idea, by the way. They can steal your information. You select 100 adults. What is the probability that exactly 35 adults believe there's no difference between secure and unsecure networks? Now, really think about what this question's asking. This question is asking us about a very specific outcome. Out of 100 people, we want to know what the probability is of exactly 35 believing there's no difference. Now, that's such a narrow window. This is not 34, not 36, but exactly 35. So the expectation is that the probability should be very low because of how specific the outcome is. Let's head over to Rguroo so that I can show you how to do this in Rguroo. Okay, so we don't need any data or anything like that. We're just going to use the probability calculator here. So you're going to be going to probability simulation, then to probability, and to the probability calculator. Now we will be working with continuous very soon, but we are still working with discrete data. And recall, discrete data is that countable data without fractions and decimals. So this is just a calculator. Okay, you have different distributions you can choose from. You only need the binomial one for this particular course, but if you take the second course in statistics, we'll work with a couple other ones. The number of trials were 100 people that we were going to ask. The probability of success, if you recall from the PowerPoint, it said that there was 26% chance that a person would indicate that they don't believe there's a difference. We want to select the equal sign because it said exactly, and exactly translates as an equal to 35. Now I don't need a graph or anything. I could, if I wanted to see the mean and standard deviation and variance of any one of these, but I really can just click the eyeball and stay in the calculator and use my calculator over and over again. And that'll give me the probability that I'm looking for. So if I move this decimal place over to translate, there's about a 1% chance that exactly 35 people out of 100 would say they don't believe there's a difference. Now, if I did want to graph it and I hit my eyeball, what this does give me is the expected value of the probability distribution. Recall that from previous sections. Okay, so the expected value is 26 out of the 100 would say that they don't believe there's a difference between the Wi-Fis. You get the variance, which you could easily translate to standard deviation by taking the square root of 19.24. And it also gives you the probability. What it also does is it maps a probability distribution for the data that you're presenting, and it will show you whether it is normally distributed, skewed left, or skewed right. And in this case, we are normally distributed for this distribution. We're not going to be doing a whole lot with distributions in this particular binomial section, but it's good to know that your calculations are very easy to get. Let's head back to the PowerPoint for our next example. The U.S. Land Management Office regularly holds lottery for the lease of government lands. Your company has won the rights to 12 of these leases. Historically, about 10% of these lands possess sufficient oil reserves for profitable operation. Construct the distribution for the number of leases that will be profitable. What is the probability that at least one of these leases will be profitable? Okay, so we need to consider first creating the probability distribution. Now let me show you how to do that in Rguroo. So when I was playing around with Rguroo, it does a good job of allowing you to stack the probabilities, but it doesn't necessarily create a pretty chart for you. You kind of have to do that on your own. It does create pretty graphs, as you can see, but not pretty charts. At least I haven't seen where it can do that. So I'm going to head back to the probability calculator, And you see this left menu here? This is where I want to store all of my outcomes. So the first possibility is that the probability of, sorry, not the probability, that the count of successes is exactly none of the 12 properties has sufficient oil reserves. So again, it's on binomial. We have 12 leases. The probability of success, they said, was about 10%, so 0.1. We are going to say equal to 0, and we're going to click our eyeball. So there's a 28% chance that none of the 12 properties will have sufficient oil reserves. I'm going to select that I save this in x equals 0. And I'm telling it that I'm going to want a graph when I graph this. You know what? Maybe I'll leave the graph out. Maybe that'll give me my chart. Let's see. I'm going to add the next one. So the next one would be that the count of successes is exactly one of the 12 properties produce sufficient oil. So again, I have to type this all in. So we have, and I wish it stayed, but when you start a new calculation, it deletes everything for you, which I'm sure in some cases that's going to be great, but in this one, it would be nice if it can keep all the numbers in there for me. All right, we're going to select equals 1 and eyeball. And that is now saved to x equals 1, new. Okay, x equals 2. So again, we have 12 trials or properties and 0.1 and equal and 2, eyeball. 23% chance that exactly 2 of the 12 properties will have oil reserves. And I didn't read this one, but notice if I click back, as I forgot to record it, if we round 38%, ooh, that's very likely that 1 is going to be sufficient oil reserves. Okay, let's add another one, x equals 3. So I'm creating my probability distribution by calculating each one of the possible outcomes with 12 leases, probability of success, and exactly equal to 3 properties. Okay, ooh, that drops dramatically to about 9% chance that exactly 3 of the 12 properties would be sufficient for oil reserves. Let's add another one, and let's do the exact count of successes being 4 of the 12 properties. Ooh, we drop down even more to 2%. Let's do 5 properties. Okay, 12.1 equals 5, eyeball. Ooh, that is less than 1% chance that 5 properties out of the 12 would be sufficient for oil reserves. Let's head up to 6 because we haven't hit 0 yet. And even if it looks like we hit 0, it's not actually 0. It's going to be a really, really tiny probability. And sometimes you'll see that we round to 0, which isn't actually correct because you never want to write 0 as a probability unless it's absolutely impossible to happen. Okay, 6 and eyeball. Ooh, now we're getting really low. We're very much below 1%. That's 2x equals 7. So to build a probability distribution, you have to run through every possible outcome for x. So every single count from 0 to 12. Ooh, okay, this is good for us to recall. So that E-5, that's the same type of notation you probably recognize from your calculator. And recall that this is just scientific notation. It is the same thing as 4.67 times 10 raised to the -5 power. And the negative tells you to move that decimal place to the left 5 places. Okay, next one, x equals 8. Just so you know, the calculator does not do this any faster. So if you're like, I want to use my calculator, this is taking too long. It's the same thing. You have to calculate each PDF separately. So there's no fast way to do this that I know of. If you know of a way, do share. Here we go. Okay, add another one, x equals 9. We're getting there. 12 trials, probability of success equals 9 eyeball. X equals 10, almost done. 12 trials, probability of success equals and 10. Notice this negative number is getting bigger and bigger, which means the decimal place is moving over farther and farther to the left, which means the probability is getting smaller and smaller as we continue. Okay, 11. 11. Very unlikely. And last one, what is the probability that all 12 properties will produce oil? And again, very, 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 very unlikely. Now, I notice that I'm not going to get a chart out of this. So let me select the graph for all of these so I can show you what this looks like. Or okay, and I'm going to hit my eyeball. Now I can scroll through. I can see that for this binomial distribution, the expected value is 1.2. That means the most likely case out of 12 properties is that a little over one of them is going to be sufficient oil supply with a variance of 1.08. Again, if you want that standard deviation, just take the square root of this number. And we can see the probability distribution is skewed left, or excuse me, skewed right this time. So we see that we have a bulk of stuff in the beginning and then it fades off. And you can even see that the graph doesn't even bother to graph out 7 through 12 because they're so ridiculously close to 0. Okay, so to answer the question about at least one, what is the probability that at least one? Well, there's two ways to do that with discrete data. I can take the probabilities of everything but 0, so at least one means one or more. So I'd take 0.3766 and I would add that to 0.2301 and so on, all 12 of these. Or I can go back to my basic calculator and I can clear this out because I want a new one. You know what? Let me actually just start a new calculator. So I'm going to go back to a calculator, discrete. I am going to say that there are 12 trials with the probability of success still at 10%. Now, to translate at least one, I'm going to say, what are the probability that it is above? And above is a strictly greater than, so I have to say above 0 in order for it to include 1 through 12, but not 0. So now I'll see that, again, the expected value is not going to change, but I can see that the probability of at least 1 is, and you can see that here, greater than or equal to. Well, that's good to know. This is using a greater than or equal to, which is not a direct translation for above, so tricky, tricky. We got to go back here and change this to a 1. So now at least 1 being greater than or equal to 1 is a 72% chance that that's going to occur. Notice by the graph, I can ensure that it is highlighting the correct values and it is leaving out 0. All right, let's head back to the PowerPoint now. So here's the table, and as I was calculating those, this is what I would do. I would list my counts of success, and I would have typed in each one of the outputs. Now notice here that they put zeros. Those, again, are not actually zeros. They're just so small they don't fit within 4 decimal places. Or you don't have any non-zero integers in the 4 decimal places. The binomial parameters are n equals 12 and p equals 0.1, which we know. And this pretty much just describes everything that I said. According to a recent national poll, about 40% of Americans believe in ghosts. Assuming this percentage is accurate, if 20 people were randomly selected and asked if they believed in ghosts, what is the probability that 12 or more would say that they do? For this problem, n equals 20, p equals zero point 0.4, and x ranges from 12 to 20 because we're saying 12 or more. That includes 12. Let's calculate this one in our Rguroo screen again. So we have 20.4 and 12 or more. So I'm going to start a new probability calculator. There were 20 trials with a probability of success was 4, I believe. Yes. No, 40. My bad. 40, not 4. And I want above 12, which will include 12. Okay, so I see that the probability of that happening, 12 or more, being 0.056, rounding to about 6% chance. And again, we can see that this distribution is normally distributed, and we are highlighting 12 or more over here. Back to our PowerPoint. Okay, so the shape of the distribution depends on the parameters n and p. If p is small, the distribution tends to be skewed right. If p is close to 50%, we tend to see a symmetrical distribution. And if p is very large, we tend to see a left skew distribution. The expected value is calculated by simply n times p. So it's a very easy calculation to do out by hand. You don't really need Rguroo to do it. You just take your count of trials n and multiply it by the probability of success. And similarly, the variance and standard deviation have very straightforward formulas as well. Remember that 1 minus p is q, the probability of failure, which is the opposite of p. All right, this concludes this video on binomial distributions.